In mathematics, binomial coefficients are a family of positive integers that occur as coefficients in the binomial theorem. They are indexed by two non-negative integers. The binomial coefficient indexed by n and k is usually written. It is the coefficient of the xk term in the polynomial expansion of the binomial power n. Under suitable circumstances, the value of the coefficient is given by the expression. Arranging binomial coefficients into rows for successive values of n, and in which k ranges from 0 to n, gives a triangular array called Pascal's triangle. This family of numbers also arises in many areas of mathematics other than algebra, especially in combinatorics. Is often read aloud as n choose k, because there are ways to choose k elements, disregarding their order, from a set of n elements. The properties of binomial coefficients have led to extending the meaning of the symbol beyond the basic case where n and k are non-negative integers. With kn, such expressions are still called binomial coefficients. History and notation. The notation was introduced by Andreas von Ettingshausen in 1826, although the numbers were already known centuries before that. The earliest known detailed discussion of binomial coefficients is in a 10th century commentary, by Haliadar, on an ancient Sanskrit text, Pingala's Chandasastra. In about 1150, the Indian mathematician Bhaskaracharya gave an exposition of binomial coefficients in his book Lilavati. Alternative notations include C, N, CK, NCK, CKN, CNK, CN, K, in all of which the C stands for combinations or choices. Many calculators use similar variants of the C notation as it can be represented on a single line display. Definition and interpretations. For natural numbers n and k, the binomial coefficient can be defined as the coefficient of the monomial xk in the expansion of n. The same coefficient also occurs in the binomial formula, which explains the name binomial coefficient. Another occurrence of this number is in combinatorics, where it gives the number of ways, disregarding order, that k objects can be chosen from among n objects. More formally, the number of k elements subsets of an n-element set. This number can be seen as equal to the one of the first definition, independently of any of the formulas below to compute it. If in each of the n factors of the power n one temporarily labels the term x with an index I, then each subset of k indices gives after expansion a contribution xk, and the coefficient of that monomial in the result will be the number of such subsets. This shows in particular that is a natural number for any natural numbers n and k. There are many other combinatorial interpretations of binomial coefficients. For instance, the number of words formed of n bits whose sum is k is given by, while the number of ways to write where every I is a non-negative integer is given by. Most of these interpretations are easily seen to be equivalent to counting k combinations. Computing the value of binomial coefficients. Several methods exist to compute the value of without actually expanding a binomial power or counting k combinations. Recursive Formula. One method uses the recursive, purely additive formula with initial boundary values. The formula follows from considering the set 1, 2, 3, n, and counting separately the k-element groupings that include a particular set element. Say I in every group and all the k groupings that don't include I. This enumerates all the possible k combinations of n elements. It also follows from tracing the contributions to xk in n-1. As there is 0xn plus 1 or x minus 1 in n, one might extend the definition beyond the above boundaries to include equals 0 when either k greater than n or chi less than 0. This recursive formula then allows the construction of Pascal's triangle, surrounded by white spaces where the zeros, or the trivial coefficients, would be. Multiplicative formula. A more efficient method to compute individual binomial coefficients is given by the formula where the numerator of the first fraction is expressed as a falling factorial power. This formula is easiest to understand for the combinatorial interpretation of binomial coefficients. The numerator gives the number of ways to select a sequence of k distinct objects, retaining the order of selection from a set of n objects. The denominator counts the number of distinct sequences that define the same k combination when order is disregarded. Factorial formula. Finally, though computationally unsuitable, there is the compact form, often used in proofs and derivations, which makes repeated use of the familiar factorial function, where n denotes the factorial of n. This formula follows from the multiplicative formula above by multiplying numerator and denominator by. As a consequence, it involves many factors common to numerator and denominator. It is less practical for explicit computation unless common factors are first cancelled. The formula does exhibit a symmetry that is less evident from the multiplicative formula, which leads to a more efficient multiplicative computational routine. Using the falling factorial notation, generalization and connection to the binomial series, the multiplicative formula allows the definition of binomial coefficients to be extended by replacing n by an arbitrary number alpha, or even an element of any commutative ring in which all positive integers are invertible. With this definition, one has a generalization of the binomial formula, which justifies still calling the binomial coefficients. This formula is valid for all complex numbers alpha and x with x less than 1. It can also be interpreted as an identity of formal power series in X, where it actually can serve as definition of arbitrary powers of series with constant coefficient equal to 1. The point is that with this definition, all identities hold that one expects for exponentiation. Notably, if alpha is a non-negative integer n, then all terms with k greater than n are 0, and the infinite series becomes a finite sum, thereby recovering the binomial formula. However, for other values of alpha, including negative integers and rational numbers, the series is really infinite. Pascal's triangle. Pascal's rule is the important recurrence relation, which can be used to prove by mathematical induction that is a natural number for all n and k, a fact that is not immediately obvious from formula. Pascal's rule also gives rise to Pascal's triangle. Row number n contains the numbers for k equals 0, n. It is constructed by starting with ones at the outside and then always adding two adjacent numbers and writing the sum directly underneath. This method allows the quick calculation of binomial coefficients without the need for fractions or multiplications. For instance, by looking at row number 5 of the triangle, one can quickly read off that 5 equals 1 by 5 plus 5 by 4 y plus 10 by 3 y 2 plus 10 by 2 y 3 plus 5 x y 4 plus 1 y 5. The differences between elements on other diagonals are the elements in the previous diagonal, as a consequence of the recurrence relation above. Combinatorics and statistics. Binomial coefficients are of importance in combinatorics, because they provide ready formulas for certain, frequent counting problems. There are ways to choose k elements from a set of n elements. See combination. There are ways to choose k elements from a set of n elements if repetitions are allowed. See multiset. There are strings containing k1s and n0s. There are strings consisting of k1s and n0s such that no two ones are adjacent. The Catalan numbers are. The binomial distribution in statistics is binomial coefficients as polynomials. For any non-negative integer k, the expression can be simplified and defined as a polynomial divided by k. This presents a polynomial in T with rational coefficients. As such, it can be evaluated at any real or complex number t to define binomial coefficients with such first arguments. These generalized binomial coefficients appear in Newton's generalized binomial theorem. For each k, the polynomial can be characterized as the unique degree k polynomial p satisfying p equals equals p equals 0 and p equals 1. Its coefficients are expressible in terms of Stirling numbers of the first kind. The derivative of can be calculated by logarithmic differentiation. Binomial coefficients as a basis for the space of polynomials over any field of characteristic 0. Each polynomial p of degree at most d is uniquely expressible as a linear combination of binomial coefficients. The coefficient AC is the kth difference of the sequence p. Explicitly, integer-valued polynomials. Each polynomial is integer-valued. It takes integer values at integer inputs. Therefore, any integer linear combination of binomial coefficient polynomials is integer-valued too. Conversely, shows that any integer-valued polynomial is an integer linear combination of these binomial coefficient polynomials. More generally, for any subring R of a characteristic 0 field K, a polynomial in K T takes values in R at all integers if and only if it is an R linear combination of binomial coefficient polynomials. Example: the integer-valued polynomial 3t2 can be rewritten as identities involving binomial coefficients. The factorial formula facilitates relating nearby binomial coefficients. For instance, if k is a positive integer and n is arbitrary, then and with a little more work. Moreover, the following may be useful. For constant n, we have the following recurrence series involving binomial coefficients. The formula is obtained by setting x equals 1 and y equals 1. This is equivalent to saying that the elements in one row of Pascal's triangle always add up to 2 raised to an integer power. A combinatorial interpretation of this fact involving double counting is given by counting subsets of size 0, size 1, size 2, and so on up to size n of a set S of n elements. Since we count the number of subsets of size I for 0 in, this sum must be equal to the number of subsets of S, which is known to be 2n. That is the statement that the power set of a finite set with n elements has size 2n. More explicitly, consider a bit string with n digits. This bit string can be used to represent 2n numbers. Now consider all of the bit strings with no ones in them. There is just one, or rather n, choose 0. Next consider the number of bit strings with just a single one in them. There are n, or rather n, choose 1. Continuing this way, we can see that the equation above holds. The formulas and follow from after differentiating with respect to x and then substituting x equals 1. The Chu-van-de-Monde identity, which holds for any complex values m and n and any non-negative integer k, is and can be found by examination of the coefficient of in the expansion of mn minus m equals n using equation. When m equals 1, equation reduces to equation. A similar-looking formula, which applies for any integers j, k, and n satisfying 0 j, k, n, is and can be found by examination of the coefficient of in the expansion of using when j equals k. Equation gives from expansion using n equals 2 meters, k equals m, and 1 finds let f denote the nth Fibonacci number. We obtain a formula about the diagonals of Pascal's triangle. This can be proved by induction using or by Zeckendorf's representation, f, without consecutive members, which also form all the numbers below f. A combinatorial proof is given below. Another identity that follows from with j equals k1 is partial sums. Although there is no closed formula for partial sums of binomial coefficients, one can again use an induction to show that for k equals 0, n-1 as well as, except in the trivial case where n equals 0, where the result is 1 instead, which is itself a special case of the result from the theory of finite differences, that for any polynomial p of degree less than n, differentiating k times and setting x equals -1 yields this for when 0 k less than n, and the general case follows by taking linear combinations of these. When p is of degree less than or equal to n, where is the coefficient of degree n in p. More generally for where m and d are complex numbers. This follows immediately applying to the polynomial q equals p instead of p, and observing that q has still degree less than or equal to n, and that its coefficient of degree n is dnan. The series is convergent for k2. This formula is used in the analysis of the German tank problem. It follows from which is proved by induction on M. Using one can derive, and series multisection gives the following identity for the sum of binomial coefficients taken with a step s and offset t as a closed-form sum of s terms. Identities with combinatorial proofs. Many identities involving binomial coefficients can be proved by combinatorial means. For example, the following identity for non-negative integers when q equals 1 can be given a double counting proof as follows. The left side counts the number of ways of selecting a subset of n equals 1, 2, n, with at least q elements, and marking q elements among those selected. The right side counts the same parameter, because there are ways of choosing a set of q marks, and they occur in all subsets that additionally contain some subset of the remaining elements, of which there are in the Pascal's rule. Both sides count the number of k-element subsets of n, with the right-hand side first grouping them into those that contain element n and those that do not. The identity also has a combinatorial proof. The identity reads: suppose you have empty squares arranged in a row and you want to mark n of them. There are ways to do this. On the other hand, you may select your n squares by selecting k squares from among the first n squares from the remaining n squares. Any k from 0 to n will work. This gives now apply to get the result. The identity has the following combinatorial proof. The number denotes the number of paths in a two-dimensional lattice from to using steps, and this is easy to see. There are steps in total and one may choose the steps. Now, replace each step by a step. Note that there are exactly. Then one arrives at point using steps, and doing this for all between n gives all paths from to using steps, and clearly, there are exactly such paths. Sum of coefficients row. The number of k combinations for all k is the sum of the nth row of the binomial coefficients. These combinations are enumerated by the 1 digits of the set of base 2 numbers counting from 0 to, where each digit position is an item from the set of n. Dixon's identity. Dixon's identity is, or, more generally, where a, b, and c are non-negative integers. Continuous identities. Certain trigonometric integrals have values expressible in terms of binomial coefficients. For these can be proved by using Euler's formula to convert trigonometric functions to complex exponentials, expanding using the binomial theorem, and integrating term by term. Generating functions. Ordinary generating functions for a fixed n. The ordinary generating function of the sequence is, for a fixed k, the ordinary generating function of the sequence is, the bivariate generating function of the binomial coefficients is, another bivariate generating function of the binomial coefficients, which is symmetric, is, exponential generating function. The exponential bivariate generating function of the binomial coefficients is. Divisibility properties. In 1852, proved that if m and n are non-negative integers and p is a prime number, then the largest power of p dividing equals pc, where c is the number of carries when m and n are added in base p. Equivalently, the exponent of the prime Pn equals the number of non-negative integers j such that the fractional part of k, pj, is greater than the fractional part of n, pj. It can be deduced from this that is divisible by n, gcd. In particular, therefore, it follows that p divides for all positive integers r and s such that s less than pr. However, this is not true of higher powers of p. For example, 9 does not divide. A somewhat surprising result by David Singmaster is that any integer divides almost all binomial coefficients. More precisely, fix an integer d and let f denote the number of binomial coefficients with n less than n such that d divides. Then since the number of binomial coefficients with n less than n is n2, this implies that the density of binomial coefficients divisible by d goes to 1. Another fact: an integer n2 is prime if and only if all the intermediate binomial coefficients are divisible by n. Proof: when p is prime, p divides for all 0 less than k less than p because it is a natural number and the numerator has a prime factor p but the denominator does not have a prime factor p. When n is composite, let p be the smallest prime factor of n and let k equals n, p. Then 0 less than p less than n, and otherwise the numerator k times has to be divisible by n equals k times p. This can only be the case when times is divisible by p, but n is divisible by p, so p does not divide n-1, n-2, n-p plus 1, and because p is prime, we know that p does not divide times, and so the numerator cannot be divisible by n. Bounds and asymptotic formulas. The following bounds hold. For 1kn, Stirling's approximation yields the bounds, and, in general, for m2 and n1, and the approximation is for both and much larger than 1. Stirling's approximation also yields the following asymptotic approximation, where is the binary entropy of. More precisely, for all integers with, we can estimate the sum of the first binomial coefficients as follows. When is large and is much smaller than, one can also write, and therefore if more precision is desired, one can approximate with an integral, obtaining for m, and these approximations yield 12.312 and 12.133 respectively. The infinite product formula yields the asymptotic formulas is. This asymptotic behavior is contained in the approximation as well. Further, the asymptotic formula hold true, whenever and for some complex number. A simple and rough upper bound for the sum of binomial coefficients can be obtained using the binomial theorem. Approximations. For large values of n, the following gives an approximation of the binomial coefficient based on its relation to the normal distribution. This follows from the bounds on the central limit theorem. Taking a normal distribution with the same expectation and variance as the binomial distribution, centering the probabilities, by setting p equals 1, p equals 1/2, and multiplying both by 2n.